Welcome to the Agile Software Engineering Deep Dive. My name is Alessandro Guida, and in this episode I want to talk about something we often assume we've already outgrown in modern software engineering. Design principles. Solid is sometimes treated as something from another era. Useful ones, but less relevant in a world of microservices, cloud platforms, and AI-assisted development. But complexity hasn't disappeared. It has only changed shape. Coupling still slows teams down. Unclear responsibilities still create bottlenecks, and systems still become fragile when their design can no longer be explained. In this episode, we'll revisit the solid principles, not as academic rules, but as practical tools for managing complexity in modern systems. We'll explore why single responsibility still matters beyond classes, how open/closed thinking enables safe evolution, and why principles like Liskov Substitution and Dependency Inversion now show up at API and system boundaries. This is not about writing perfect code or following rigid rules. It's about building software that teams can understand, change, and trust long after the original developers have moved on. Because while tools, frameworks, and platforms evolve quickly, the cost of poor design decisions compounds quietly over time. Let's dive in.
Welcome back to the Deep Dive. We've got a stack of research today that, at first glance, feels a little bit backwards.
Backwards? How so?
Well, just look at the landscape right now. We are living in this golden age of speed. We've got AI writing functions in seconds. We've got serverless architecture spinning up and down automatically.
Yeah, everything is instant.
It feels like we're living in the future. But the sources you brought to the table, they're telling us the secret to surviving this future is to look back at the late 90s.
It does sound counterintuitive, doesn't it? Like telling a Tesla driver they need to learn how to shoe a horse.
Exactly. We're talking about the solid principles, SOLID. And I have to be honest, for a lot of people, that acronym probably triggers flashbacks to like a dry computer science lecture hall.
Oh, for sure.
It sounds academic. It sounds like pure theory.
I get that. It has that eat your vegetables vibe, like rules for rules' sake.
Right. But our mission today is to unpack why this isn't just some dusty old theory. The argument in these articles is that these principles are actually a survival guide for modern engineering, and that if you ignore them, all that AI speed and cloud power just helps you build a disaster faster.
That is the perfect way to frame it, because here's the thing about technology. History tools constantly change. We change languages, from Java to go to Rust.
We change clouds, frameworks.
Every 18 months. But good design, that turns out to be timeless.
Why is that, though? Why doesn't design expire like a JavaScript framework?
Because the solid principles weren't really written for computers. I mean, computers don't care if your code is messy. They just execute the binary.
Right.
They will happily run a million lines of spaghetti code. These principles were written to address how humans manage complexity. And, our brains haven't upgraded much since the 90s.
That's a humbling point. We're still running on the same hardware up here.
Exactly. So just to set the stage historically before we dive in, these concepts were largely formulated by Robert C. Martin, Uncle Bob, back when object-oriented programming was really finding its footing.
Okay.
He saw teams building these massive, rigid systems where they were terrified to change anything because it would break something else. Later on, Michael Feathers, who wrote the book on legacy code, he arranged them into the acronym SOLID.
SOLID. 5 letters, 5 guardrails. And what I found so cool in reading through this material is that even though they were written for classes and objects, the research argues they are the secret DNA behind things like Kubernetes.
It's fractal. The same rules apply at the micro level and the macro level.
So let's get into it. The S, the single responsibility principle.
La foundation.
The definition is pretty punchy. A class should have only one reason to change, but I want to push on that. One reason to change. What does that actually look like?
So in the old days, we warned against the God class. You know that file.
Oh, I've definitely seen it. utils.java or manager.js, the file that's 4,000 lines long and nobody knows who wrote it.
Right. It handles business logic, and it talks to the database, and it formats emails, and it logs errors.
And it probably validates user passwords, too. It does everything.
It's the file everyone on the team is afraid to touch.
Precisely. And the reason you're afraid to touch it is that it has too many reasons to change. If the marketing team wants to change the email format, you have to open that file.
Mm-hmm.
If the database admin changes the password requirements, you have to open that same file.
And since everyone is opening that file for different reasons, the merge conflicts are a nightmare. You're stepping on each other's toes constantly.
You have high coupling and low cohesion.
The single responsibility principle says, no, split those up. The thing that formats emails should only worry about formatting emails.
But let me play devil's advocate here. If I take my one big file and split it into 10 little files, haven't I just made it harder to find things? Now I have to jump through 10 tabs to see how it works.
That is the most common pushback I hear. I don't want to hunt through folders. But think about it in terms of fault isolation. If you have a God class and you make a typo in the login code,
Oh no.
you might bring down the entire checkout process.
Ouch. So a minor error becomes a catastrophic failure.
But if your logging is a separate single responsibility module and it breaks, maybe you just lose some logs, the checkout process keeps running.
Okay.
And this is where it connects to the modern world. This is the entire philosophy behind microservices.
Connect those dots for us. How does a principle for a class apply to cloud architecture?
Well, if a microservice is doing too much, say it's handling user auth, A&D processing payments, and generating PDF reports, it becomes a bottleneck. It's a God service.
And if the PDF generator gets stuck or runs out of memory?
Nobody can log in.
So single responsibility isn't just about organizing code. It's about keeping failures contained.
It's about creating fire breaks in your system. Whether it's a function or a whole server, if it has one job, you know exactly where to look when it breaks, and you know it won't take down the rest of the ship.
It stops the murder mystery aspect of debugging.
Oh.
Okay, let's move to O, the open-closed principle.
This is one of my favorites, but it's arguably the hardest to explain to a junior engineer.
It definitely sounds like a riddle. Software entities should be open for extension, but closed for modification.
It's a paradox, right? How can a door be open and closed at the same time?
Exactly. If I can't modify it, how can I extend it? It sounds like you're telling me don't touch the code, but also add new features.
The best way to visualize this is to think about a web browser like Chrome or Firefox. The browser is closed for modification. You, as a user, cannot rewrite the C++ code that renders web pages.
Right, I can't change the source code of Chrome.
That core is locked down, compiled, and shipped. But it is open for extension.
Through extensions.
You can install a password manager, an ad blocker, a theme. You are adding new behaviors to the browser without touching the core engine.
Okay, that clicks. So in software engineering, we want to build systems that act like that browser. A core that doesn't change, but with places to plug things in.
Yes. Imagine you're building a system to calculate payroll. You have a class that calculates taxes for U.S. employees.
Yeah.
Now the company expands to the U.K.
The bad way to handle this, and I've definitely done this, is to open up the calculate tax file and start adding messy if-else statements everywhere. If UK do this, if US do that.
Exactly. That is modifying the core. Every time you touch that core file to add a country, you risk breaking the calculation for the U.S. employees.
You're performing open heart surgery every time you want to put on a new hat.
I love that imagery. That's exactly it. So the open-closed way would be what?
It would be, I guess, designing the system so that tax strategy is a plug-in or an interface.
Right. You write a new class for UK tax, you plug it in, you never touch the U.S. tax code, it remains closed.
You add code to add value. You don't change existing code to add value.
And think about what that does for your stress levels.
Yeah.
If you aren't changing the old code, you don't have to retest the old code with the same level of paranoia.
This seems crucial for continuous delivery.
It's the only way continuous delivery works at scale. If you have to patch the base code every time you want a feature for a specific client, you are creating a nightmare of forks and versions.
That's not agile.
That's technical debt. The open-close principle is what allows you to innovate around a stable core.
All right, let's move to L, the Liskov Substitution principle.
Barbara Liskov. She introduced this in 1987. It's actually one of the older concepts in the stack.
And the definition is, subtypes must be substitutable for their base types. Now, I'm going to be honest, this is the one that usually makes people's eyes glaze over.
Yeah, it's the most technical sounding one. It comes from type theory.
The source material uses the classic square versus rectangle example. Can we walk through that briefly? Because I think it actually highlights the problem well.
Sure, it's the classic example for a reason. So in geometry, a square is a rectangle.
Right. It's a rectangle where all sides are equal.
So in code, you might think, great, I'll make a square class that inherits from the rectangle class. But here's a catch. A A rectangle object generally promises that you can set the width and height independently.
I can make it 10 wide and 5 high.
But a square enforces that width and height are linked if you set the width to 10.
The height must become 10.
Mm-hmm.
Okay, I see where this is going. If I have some code, maybe a layout engine, that expects a rectangle, and it sets width to 10 and height to 5,
And you hand it a square.
the square changes the height to 10 behind my back.
And now your layout is broken. The square was not substitutable for the rectangle because it changed the behavior in a way the parent class didn't allow.
So Liskov is about keeping promises. If the parent says, I can do X, the child can't suddenly say, actually, I can't do X.
It's about trust. And if we zoom out to modern tech, this is absolutely critical for APIs and microservices.
How does it apply to APIs? Because that's what most of us are building today.
Imagine you have a microservice that returns a user object. And in version 1, the user ID is a number.
Okay, simple enough.
Thousands of other services are consuming your API, expecting that number. Then you release version 2. It's a subtype of the service. But you decide, hey, we need alphanumeric IDs now, so you change the ID to a string.
And you just crashed 1,000 downstream systems.
You violated Liskov. You broke the contract. The consumer could not substitute version 2 for version 1 without breaking.
So when we talk about backward compatibility, we're really talking about Liskov substitution.
We are. It's the principle that allows modular parts to be swapped out. If I can't trust the component I'm plugging in to behave like the old one, I have to rewrite everything.
Which destroys reuse.
Yeah.
I feel like we've all been burned by a library update that did exactly this.
Oh, absolutely. It's the reason developers have trust issues with updates.
Okay, let's go to I, the interface segregation principle.
Clients should not be forced to depend on methods they do not use.
This one feels like it's about decluttering. The source material makes a joke about bloat carrying around baggage you don't need.
Think of it like a Swiss Army knife. It's a cool tool, right? It has a knife, a saw, a corkscrew, a toothpick.
But usually I just need the knife.
Right. But imagine as, in order to use the knife, you were forced to hold the saw, the corkscrew, and the magnifying glass all open at the same time.
It would be heavy, awkward, and frankly dangerous. I'm trying to gut an apple and I'm stabbing myself with the corkscrew.
Interface segregation says, don't build Swiss Army knives. Give me a knife. Give me a corkscrew. Let me pick up only what I need.
In modern web development, where do we see this going wrong?
REST APIs are the biggest offender here. Imagine you're building a mobile app and you need to display a user's name on the profile screen. You call getUser.
And the server sends back the name. Plus, their entire purchase history, their bio, their image URL, their last 10 login times.
Exactly. You downloaded 50 kilobytes of JSON just to get the string John Doe.
That's wasteful.
It's incredibly wasteful. It hurts battery life on the phone, it eats up data plans, and it creates tight coupling. If the backend changes how purchase history is formatted,
My app might crash trying to parse the JSON, even though my app never used the purchase history.
you depended on data you didn't need. This explains the rise of things like GraphQL, doesn't it?
Yes, exactly.
GraphQL allows the client to say, I only want the name. It forces interface segregation. Good design focuses on consumer needs, not the convenience of the person building the backend.
I hadn't thought about the energy angle. But yeah, sending useless data across the world millions of times a day, that adds up.
It does. Good architecture is actually more energy efficient.
Okay, final letter. D. Dependency inversion.
Flipping the script.
The definition. High-level modules should not depend on low-level modules. Both should depend on abstractions. Okay, translate that for us. That is a mouthful.
In simple terms, don't hardcode the details.
Give us a real-world analogy.
Imagine a lamp and a wall socket. The lamp is your high-level logic. It produces light. The power plant is the low-level detail.
Okay.
You don't solder the lamp directly to the power lines in the street.
No, that would be inconvenient. And probably illegal.
You use a plug and a socket. The socket is the abstraction. The lamp doesn't care if the power comes from a nuclear plant, a wind farm, or a diesel generator.
It just cares that there is a standard socket that provides 120 volts.
So in code, if I'm writing an app to process orders, my code shouldn't say, write this to an AWS Aurora database.
Right, because AWS Aurora is the nuclear plant. It's a specific implementation detail.
Your code should just say, I need to save this order. That is the interface, the socket, and then separately we plug AWS into that socket.
And if you hard code the dependency on AWS,
Uh-huh.
and then next year the company decides to switch to Azure or Google Cloud,
You have to rewrite your entire application. You soldered the lamp to the street.
that is a vivid image. But here's where I want to dig deeper. The source mentioned test doubles and mocking. Why is dependency inversion so important for testing?
This is the holy grail aspect. If your business logic is hard-coded to a real database, running tests is slow and dangerous, you might accidentally delete real data.
Or you have to wait 20 minutes for the test suite to run because it's talking to a real server.
Exactly. But if you use dependency inversion, you can plug in a fake database for testing, just an in-memory list that runs instantly.
You swap the nuclear plant for a AAA battery. I love that. So you can test the lamp without needing the grid.
Perfectly put.
So we've covered the 5 principles, but here is where the deep dive takes a turn that I really loved. We usually talk about solid in terms of like Java code,
Yeah.
but the research points out that if you look at modern infrastructure, specifically Kubernetes, it's basically a shrine to solid.
This was a real aha moment in the reading. We tend to think of infrastructure and code as separate worlds, but Kubernetes works because it enforces solid at the infrastructure level.
Okay, prove it. Walk us through the S in Kubernetes.
Single responsibility. Look at the pod or container. The golden rule of containers is one process per container.
Right.
You don't shove your database and your web server and your background worker into one Docker image.
That's a violation of SRP. You're creating a God container.
And if you do that, you can't scale the web server without also scaling the database. You lose all the benefits. Kubernetes forces you to break them apart.
What about open-closed?
Rolling updates.
Mm.
When you want to deploy a new version of your app in Kubernetes, do you SSH into the server and change the files?
No, never. You replace the container entirely.
Right. The running infrastructure is closed for modification. You don't patch a live container. You extend the system by adding new containers and draining the old one.
It's immutable infrastructure.
And dependency inversion. This is the strongest link. In Kubernetes, a pod doesn't know where it's running. It doesn't know the IP address of the database.
It gets those injected.
Exactly. It uses config maps and secrets. These are abstractions. The infrastructure injects the details at runtime.
So the application depends on the abstraction of a configuration, not the specific server hardware.
If the hardware dies, Kubernetes moves the pod to a new server, re-injects the config, and the app never knows the difference.
So these principles from the 90s literally scale from a single line of code up to a massive global cluster.
It proves that good engineering ideas are fractal. Logic is logic, whether it's a function or a data center.
Which brings us to the deeper philosophical question the source material raises. And this is something I've been thinking about a lot. If I can just ask an AI to write my code and it spits out a working function in 3 seconds, does any of this design stuff still matter?
That is the million-dollar question. And the answer is yes, it matters more than ever.
Why? If the AI writes it, why do I care if it's solid?
Because solid isn't really about computer execution. A computer can run messy code just fine. It can run a million-line God class without complaining.
Sure.
Solid is about human cognition.
Human cognition. Explainability.
Code is read 10 times more often than it is written. If an AI generates a blob of code that works, but it violates all these principles, it's tightly coupled, it has side effects, it's a black box, what happens 6 months later?
When the business rules change.
Right. The AI might not be there, or the context is lost. A human has to look at that code and figure out how to modify it safely.
And if the code isn't solid,
The human can't understand it. Or they change one thing and the whole house of cards falls down.
it becomes legacy code the moment it's written.
Exactly. Code that violates solid is not explainable. And when systems aren't explainable, safety degrades. Innovation stalls because everyone is terrified to touch the system.
It's like building a skyscraper without a blueprint. It might stand up for a while, but you can never renovate a floor because you don't know where the load-bearing walls are.
That's it. Solid is about organizational resilience. Just like lean principles in a factory aren't just about one machine, they're about the whole plant flowing smoothly.
So it scales from a line of code to the resilience of your entire engineering organization.
And the source makes a slightly scary point. Automation doesn't eliminate design, it just hides bad design until it fails.
That's the danger. We can build bad systems faster than ever before. We can generate 1 million lines of garbage code in an afternoon.
Solid is the defense against that. It's the check that says, yes, it works, but is it maintainable? Is it robust?
So, as we wrap up, what's the big takeaway for you, our listener? Whether you're building a machine learning pipeline or firmware for a smart toaster.
The takeaway is that the essence of engineering hasn't changed. The tools are different, the languages are different, but the goal is the same, making complexity manageable. Structure and clarity are not optional.
I love that.
I would leave you with this thought. If your system works, but no one on your team can explain why it works or safely change it, is it actually a success?
Or have you just built a time bomb? That is a provocative thought to end on. So before you sign off on that pull request today, or before you design that next microservice, take a second, look at it, and ask yourself, is my design solid?
It's the question that never goes out of style.
Thanks for diving in with us. We'll see you on the next one.
Thank you for listening to the Agile Engineering Deep Dive podcast. If today's episode gave you new insight into working across teams or highlighted the role of discipline in achieving real agility, feel free to share it with your colleagues or your network. You can find the full written article along with previous episodes in the Agile Software Engineering newsletter on LinkedIn. And if you have thoughts, questions, or examples from your own organization, I'd be happy to hear from you. Your experiences help shape what we explore next. Thanks again for tuning in, and I'll see you in the next episode.